Hello, my name is Jose Martin-Garcia, and I will be talking about Geo Computation. We will be talking about new additions and the functionality to support all the Geo Computations in the Wolfram language. I'm going to talk about another of the main parts of the Geo project, which is Geo Computation. So geocomputation is a very general term, and we could include virtually everything here. But for us in the Wolfram language, because we have so many other functions outside the geo functionality itself that do many things, we can concentrate on a smaller set of things. So the fundamental aspects of computation in the Geo project are first everything that relates to measuring and computing distances, areas, angles, things like on checking membership or something inside something, this sort of thing. Then we have another aspect, which is cartographic geoprojections. This is a very important part of the system because it's going to determine very much the actual shape of the final map. Then we have geographics itself. Geographics is the basis of virtually everything in visualizing geodata. And it has a lot of computation inside, in the estimations of things, in deciding resolutions, how many points do we need to convert a geocircle into a standard graphics primitive, this sort of thing. And then there is the geophysical modeling, in the sense of having data and computation about the gravitational field. We have now tides information, recently, magnetic field, etc. But I'm not going to go into that. The functionality has been improving steadily in versions 10, both in coverage and speed. And in the recent versions, we have focused a lot in making geographics more robust and fast. And the main recent driver for this effort has been the new function GeoImage, because geographics was very much based on texture, and we cannot use that in GeoImage, so we had to change a number of things in order to support GeoImage with basically the same functionality that is behind geographics. So my plan for this talk is first to summarize the existing functionality, like Francisco did for geodata. It will just be a slide. Then I will present a couple of functions which are recent. Well, actually, one we just added, and the other one we will be just adding. And then I thought that in this talk, I would address a number of frequent questions that come to us, so things that have been asked frequently recently. Okay, so with respect to measuring, we have our main player here is geoposition. I wanted to express how flexible geoposition is. It can be added, or it can be used basically as some sort of pre-processing function, because you can pass lat long to geoposition, but also lat long heights. You can add dates here as absolute times in GMT time zones, so that geoposition doesn't have to worry about time zones. You can add lists of those positions. This is very flexible because you can have all data here numerically packed, so it's very fast for computation. And then, of course, we have the datum argument, which is very flexible, and it allows a number of models of the Earth and also using other celestial bodies. But I talked a lot about datums last year, so I'm not going to go into that this year. Just as an example, you can see here how geoposition is able to take simultaneously numeric data, parsing various forms of string input in various forms, quantities as well in various units. It will fetch data for entities, etc. It will be all translated into a single form. It can extract data from images. It can access real-time data, like the current position of this International Space Station, or, as I said, data in other planets and moons. The only restriction is that the dimension has to be consistent. So, for example, here all points have 2 lat long. Here we have 3, here we have 4. So we can mix these dimensionally different data. Other than that, if they are in the same body, you can mix them in an array, and it's recommended. There are other specifications for locations, but I'm not going to go into that today. Then with respect to Geo Computation itself, we have different types. We have the fundamental geodetic computation based on geodesics, and we have these functions to compute distances, directions, to start from a place and go to another one. So for example, if we are here in Champagne, and we want to go to the 0, 0 of lat-long coordinates, we have to move more than 6,000 miles along a geodesic. And interestingly, we have to start nearly east, only less than a degree from east. But that's the direction we have to start in order to arrive geodesically at the 0, 0. We have other types of measures for lengths, areas, lateral bounds, etc. Yes, and another thing that I wanted to stress here is that some of these computations are local. They are performed in your own machine, so that's quite fast. Other computations, like what Francisco was presenting before, travel directions and geoentities-related stuff, which is very entity-based, we do this in the Geo server itself. So we transfer our information to the Geo server so that all the entities are processed there, and we perform the computation there and bring it back. So this has advantages sometimes when you're handling lots and lots of entities, but when there are a few, the overhead of the transmission may be larger than the actual computation. So for example, to avoid that, we have added support for geoposition in recent versions, since 11, for nearest. So nearest now can do part of this, and the computation will be local. So it's a lot faster. So for example, here, geoposition, we extract all the positions for the capitals of the states, of the United States. And nearest can say, what's the closest capital to here, right? And you see, these computations are all performed already with the geoposition data. So we don't need, the entity data has been processed. That's why nearest can do it. And just to show you a difference here in timing, so we start with, say, 1,000 random points here. Nearest will find which one is the closest to us in milliseconds, while sending all these 1,000 points to the Geo server, do a computation, and bringing it back will take like 3 seconds. Okay. Well, so that was my very quick summary of what we have. So as Francisco's, in relation to fundamental geocomputation, as Francisco mentioned, GeoImage is probably the main new thing we have recently. And it works very much like geographics, except for 5 important differences. First of all, the output is an image, not a geographics object. Geographics is basically a graphics itself. And so, yes, because image doesn't have a notion of meters or any other units other than pixels, so now it will decide itself which the size of the result, rather than we controlling it from geographics. Another important difference is that Stephen wanted your image to be always satellite by default rather than street map, as geographics does. The default sorry, this is not geostyling, this is geoprojection. The default geoprojection for GeoImage is Mercator, rather than this automatic choice that geographics does, right? So this is because nearly all other systems use Mercator, so we wanted to align our images with what the actual provider sent us. Yes, so GeoImage allows itself to automatically switch to the digital globe provider when you ask for a deeper zoom. So in geographics, if you want something very deep, something a very low scale, like kilometers, it will complain it doesn't have it. You have to manually say, I want to use GeoServer goes to digital globe here. But in GeoImage, by default, it will use digital globe for very low scales. And for larger scales, like this one, it will be using our own tiles. So there's a transition there, and that's why for the whole world I have to use this. It's also because I wanted to use satellite with the labels, so I don't know whether you see them, but this has labels here for the countries. Okay, so that's an image. And as I was saying before, GeoImage has motivated a restructuring of much of geographics to process all the tiles and the image internally in a different way so that the results can be shared with GeoImage. Okay. A recent function we have added, which is simple but quite useful, is Geo Antipode. So Geo Antipode, let's see if the connection, yeah, it's working here. So Geo Antipode is just going to compute the antipode to a given location, if you give a location, which is just flipping the sign of latitude, and then longitude, it will either add 90 or subtract 90, depending on the sign of the original thing. Like geoposition does, it will collapse entities into a geoposition first, and then return the antipode for that. And in Spain, we all know that Madrid has its antipode in New Zealand. It's a very famous fact there. On geo primitives, it will try to get to return another primitive if it can. If not, for example, with a polygon, it will just flip all the coordinates in the polygon. For the day hemisphere, for example, by definition, the night hemisphere is the antipode of that. Now we can flip that, and for example, again, here we see how New Zealand, when computed the antipode, falls very much on Spain. We can do that, for example, for Antarctica, right? So we are now computed the antipode of the polygon of Antarctica, so now we see how Antarctica would look on the North Pole. We can do that even for the whole world, and so we can compare where I don't know, the United States would fall there, the ocean. And for example, Francisco was mentioning there before North Korea. So if you wanted to be very, very far from North Korea, you should go to South America. Okay. The new function we are going to have very soon is called GeoRotate. And what GeoRotate does is basically taking any position or polygon on the Earth and move it somewhere else based on a three-dimensional rotation. So remember, we have three parameters there. So for example, if we take the polygon of the US and we rotate it, this is the language. It's basically saying, well, take the geodesic that goes from here to Paris, which is that one. So then it will just move the, basically parallel transport the polygon of the US until there, and in the process it will get rotated. That's because we are only controlling two of the parameters of the rotation. We can add a third parameter that would rotate it back to the orientation you want. So this can be always done for any projection. So I don't know. It's very typical to talk about, for example, let's see if this works. Yes. So how different projections affect the shape of a given polygon. So we can play and see how the United States, it will be able to cover Greenland, for example, right? Or if you move it closer to the equator, it will look smaller than it typically looks, or in comparison with Australia, for example. As I was saying, a 3D rotation has 3 degrees of freedom, and the general language to control that is to specify the point, which is kind of the axis of rotation, plus the rotation you want to rotate around that axis. So we can do that, and what we end up with is this sort of thing. So if I start, no, I'm going the other direction. So if I start with the polygon of the US here, right, and I rotate around the North Pole, well, it's going to rotate horizontally, right? That's fine. But now, if I change the axis of rotation, so I bring it down, like I don't know, like there, then I can start again from the original polygon, which is there. But now, when I move it, you see, it will be following this path between two new parallels, right? And note how this northeast part of the US is always perpendicular to the parallel, right? So the rotation is happening just to keep that, to keep the orientation. so that the northeast part keeps being perpendicular. That's the origin of the rotation we were seeing before. And you can, this allows you, these three parameters allow you a fully general 3D rotation on the Earth. So that's your rotate, and it will be coming soon. My plan for the rest of the talk is to address one of these questions that have been asked a number of times, which, for example, one is, well, what is the meaning of the coordinates that you plot in the final map, and how can I make that to be miles, for example, right? So that's controlled with this option of the projection, which is called reference model. And by default, we have there 1, which means that when you plot a map, typically when you activate the ticks with frame true, you see the ticks here, it will say 1, 2, right? This will be of order 1. Right? This is pretty much random choice, just for homogeneity. But if you want to use miles, what you have to do is to put there the number of miles corresponding to the radius of the Earth. Right? And then once you do that, so we compute the radius of the Earth in miles, which is that number. We put it there. Reference model goes to that. Now this map will report miles here. Now, most maps distort distances, so you cannot trust these distances everywhere. So typically there is a region of the map for the orthographic projection is the center, this region here, in which distances are correct. But if you go farther from that region, the distances will not be correctly reported. So for example, for some projections, there is something called the standard parallels, which allow you to specify where those lines of proper measuring are. And those are called standard parallels. So for example, for the Albers projection, there are these two lines. So we have again the ticks being miles, right? So these miles are correct, but are correct only along those lines. And I can choose which two lines. So you see the map will change shape and depend so that those two lines are correct. So if they are equal, the map will look kind of azimuthal, etc. So depending, but you always have one line which is correct, or two. Yeah. And by the way, you see how when I'm moving this, the full map is being reprojected. There is an image transformation of the whole map, etc. And that's one of the things which we have made recently. So this is now smoother experience when we use manipulate with geographics. Second question, which I get very frequently, is how do I get a square map? Because the maps in geographics are very much controlled by the geo range. And of course, when you specify, say, 6 degrees of geo range in Italy, fine. In the equirectangular projection, which is faithful to lat long, that's a square map. But that's not the proper shape of Italy. Right? That's very compressed vertically. So the proper shape is this one. But now, this is much longer than this one, even though it's still representing 6 degrees. 6 degrees of lat long. Just that these coordinates are now different coordinates. So how do you do that? How do you get a square map of this region? Well, the way to do this is to control the map via the plot range, which is the range of the projected map. And so you do that by extracting the projection corresponding to that region, which was decided by geographics. And now you say geographics of those projected coordinates, and now you have full control on the size. Now you see you now have 6 with this option. And now this map is fully square. Of course, it's going to be a smaller region, but it's fully square. Right? So that's how you control the aspect ratio of the final maps. You can do this, for example, for any other aspect ratio. So now if we want 2, aspect ratio 2, so this is double distance than this, then we just have to say, well, horizontally I want 12 units here, and vertically I want 6. So that now is respected because this is the plot range, not the geo range. And this trick works in absolutely any projection. So for example, this is the Winkel triple projection now, with VR coordinates here, because I'm still keeping the reference model goes to 1. I extract the projection from the map because geographics chooses automatically some parameters like this one. And I put it back. But now I control the shape of the final map with the plot range. Right? And now this map, again, is fully square. Yes. So for presentations and always for our marketing pages, etc., that we want all the result be in square, etc., this is a very frequent question. Another frequent question is, what's the difference between line and Geo Path? Yes, this also appears very frequently. So here I'm going to take the same two cities, Oslo and Chicago, and I'm going to draw 3 lines. One is a geodesic, another one is a ramp line, a loxodrome, another one is a pure line, what we call line in graphics. If I put them in the map, we see red is the geodesic, blue is the straight line. Line is always straight. Geopath will be generically be curved. And now this is the loxodrome. I can put them in other projections, and you see even the positions change. So here the blue line is in between the other two. Here the blue line is over the green line. Here is under the green line. Here is over the other two. So it changes a lot. But the important thing is that, for example, notice how the geodesic always goes through Iceland and Greenland, Iceland and Greenland, Iceland and Greenland, Iceland and Greenland, right? So these are really physically defined. The line is just a straight line. And this problem is even worse for polygon. If you give 3 points and you ask for a triangle, you get that one, but the geodesic triangle is that other one, the red one. They don't even touch it. I mean, they don't even overlap at any point, right? So there is a big difference between geodesic triangles and triangles. And we control that always using the difference between line and geopath. And again, I can change the projection, and now they fully overlap. So this depends a lot on the projections. You always have to think what you want to do, right? Whether you want something on the Earth or something on the map. So you have the data there. And then the final question I have here is, again, the difference between geocenter, centering, and grid origin. So we have these 3 parameters that control very related things, but they are different, actually. So, for example, I'm only looking here at the longitude. This is the GC long is the where do I have it? It's here, the geocenter, right? So the geocenter defines the center of the region I want to see. So you see that's always kind of in the middle of the region of the Earth I'm looking at. Then we have lone zero, which is what is at the center of the coordinates. So you see how this blue point stays the same. That's the lone zero, and is what is here at 0, 0. The point of the Earth that will fall at 0, 0. And then the other one, the grid origin, is just a shift of the whole thing. So in a sense, the centering is always mapped to the grid origin. So controlling these things allowed me to, for example, again, let's go back to Korea and draw North Korea. Let's draw like a number of geocircles of different distances around North Korea, which start there, and then this is 2,000 kilometers, 4,000 kilometers, 6,000 kilometers, etc. For example, if we change to another projection, this is going to be a nicer way to understand what's going on and what are equivalent distances, but still, because your Lambert azimuthal makes an effort to preserve areas, we don't get a proper representation of distances. While now, with another projection, which is azimuthal equidistance, these circles are all of corresponding radiuses, and now it's easier to understand. And we see how it's South America, which is being stretched here as the farthest thing from this central point. Right? So again, you see how different projections allow you to visualize things in different ways. And yeah, that's it. That's exactly 25 minutes. Thank you.